Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a new topic regarding the power transmitted through nozzle. In our previous lecture, already we have discussed regarding the flow through nozzle, and now we'll discuss about the power transmitted through nozzle. Actually, this fluid flow through nozzle also related to this power transmitted, because we need to identify the power required here or power transmitted here. So for that, we require the value of velocity, what we have discussed in our last video lecture. So before starting this one, let me give a reminder of our previous lecture, what we have discussed. We have taken a large container, and from this container, there is a pipe, large, long pipe is connected to this, and at the end of the pipe, there is a nozzle is fitted to this one, and through this nozzle, the water supposed to fluid supposed to come out, which is present in the this large reservoir, or you can say the tank. So these things actually we have discussed in our last lecture. Just I'm giving a reminder of that. So from this container, that fluid which is present, let's suppose this is water, and this is large pipe is there. And this is the though this is a lengthy pipe, we can give a breakage. There is a breakage in this pipe. Breakage in the sense that indication of breakage is, that means it is a lengthy pipe. In the turbine case, we used to call this is a penstock. Okay, and at the end of this pipe, there is a nozzle is connected. This one to increase the flow velocity here, and this is the diameter of this pipe, D. You can say, and total length of the pipe is this one, L, and this is the inlet of the pipe. This position is inlet of the pipe. This one we can write inlet, and this is total fluid level. At this inlet of the pipe, if we consider this is the central line of this fluid flow in the pipe, so at this inlet position, this is the total head is present at the inlet condition. So this one we can mark it as a capital H, and this is L, and the fluid which is flowing through the pipe, this is capital V, and the fluid which is coming out from this nozzle, that is small v, we need to consider. Okay, and the diameter of the nozzle also we need to consider, this is small d, and here it is capital D. So these are the terminologies are used in this. Now in the last lecture, what we got from the derivations, we got the velocity value small v equal to, we got this equation like root over of 2g h divided by 1 plus 4f L by d into a square by capital A square. So this is the equation what we got in our previous derivations, velocity value, the velocity of the fluid which is coming out from the nozzle. And to find out the flow rate or to find out the discharge from this, we can just multiply A into B so that we can get the discharge. Now for this condition, the power transmitted through nozzle, we need to first identify what is the kinetic energy here at this nozzle part, because what are the energies are present during this fluid flow, all this energy will be converted to kinetic energy when it is coming out from the nozzle. Okay, so that means the pressure energy and velocity energy used to present in this fluid flow. So the pressure energy also will be converted to kinetic energy. So first things, let me write the kinetic energy of the jet. Jet in the sense the fluid which is coming out with from this nozzle, that is called jet. So kinetic energy of the jet at outlet of nozzle. So this one we can write as for the kinetic energy formula, we can write this is of mv square. So velocity, the way velocity of the liquid or fluid which is coming out from here, and mass of the liquid. So the mass of the fluid or liquid which is, this also we can identify the mass of liquid at the outlet of the nozzle per second, mass of the liquid per second. This one we can write, this is rho AV, or we can say this is rho Q. Okay, any one we can write, rho AV or rho Q we can write. Just put this value in this equation. So what we'll get, again just write down the kinetic energy of the jet at outlet per second. Kinetic energy of the jet at outlet per second. This one we can write, just put this value of mass per flow rate per second, this one value in place of m. So we'll get this is half rho a v into v square, that is rho a v cube. So this one you give equation 1, this is equation 2. So next, what is our intention? Our intention is to find out the power transmitted at the outlet in the nozzle. So now we'll write the power at the outlet, the power at the outlet of the nozzle equal to the same thing what we'll get, because this is the energy in terms of power which is coming out at this point. So the power at the outlet of the nozzle is nothing but what we got, the kinetic energy per second value, what we got we can write. So if you want to write in terms of power, like kinetic in terms of kilowatt, so this one also just to multiply here 1 by 1000. Okay, so what is the value of this? We can write this 1 by 2 rho av cube divided by 1000. Okay, now we'll find out the efficiency of power transmission. The efficiency of power transmission through nozzle. So efficiency equal to, we know that output by input. So here output means what are the output from this nozzle it is coming out, or what is the power at the output it's coming out. So here I will write power at, here you can write the power, okay, power at the output equal to power at inlet, outlet or inlet we can write. Now power at the inlet, output equal to what, or outlet equal to what, this one we got. So this one will write this half rho a v cube by 1000. Similarly, what is the power at the inlet condition? Inlet condition means at this point. At this point, what is the power required? So at this point also we can write, this is the formula also, like same thing, rho, we can write here rho q, what was there, into g into h, what is the head present here at this point, what is the energy present here, okay, multiply of gravity divided by 1000. This also we need to write in terms of kilowatt. So this 1000 will be cancelled and rho will be cancelled. AV is there. So as I told you, AV equal to Q. So here AV you can write and Q can be cancelled here. One only V square will be there. So here what will get 1 by 2 GH into this one we can write what? We can write 1 by 2 V square, because VQ is there, this VQ, one V will be cancelled, like means AB equal to Q, so only V square will be there. So this one we can write V square by 2GH. Now in a previous equation, like yesterday what we got in our previous lecture, so there we have seen this V equal to this formula we got. Now if I want to write this is V square by 2GH, that means V square means first root over will be gone, then V square by 2GH will be taken to this side. So what will get here 1 by, so this one also we can write 1 by 1 plus 4FL by D into A square by A square. So this one we can write, so let's write this one 1 by 1 plus 1 by 1 plus 4FL by D into A square by capital A square. So let's write this 1 by 1 plus 4FL A square by capital A square into D A square by A square. So this is our equation what we got for the efficiency one. Now make a equation number also for this. This is equation number, suppose 3 here. Now this is about the power transmitted through nozzle. Next what we'll get, next we'll discuss about the condition for maximum power transmitted through this. This is the final equation for out. Okay. Now one more condition we'll discuss about this now. What is the condition for maximum power transmitted? Maximum power transmitted through nozzle. Through nozzle. Okay. Now to identify this one, we need to see like what is the head at this inlet point, what is the head at this outlet point, and what is the loss of head during this pipe flow. So for that we know that already previously from the previous lecture also you can see that one, the same thing I have written there. So the head, the total head at the inlet of the pipe, so that is H, which is mentioned here, H, the total head at the inlet of the pipe, this equal to, or you can say this equal to, let's write this one, this equal to the head at the outlet position, the total head at the outlet position minus, no, this is plus will be there because the losses which is coming out, this includes this one, so plus HF. HF is the loss of head during the fluid flow. So what is the loss is happening during this fluid flow? If you add with this one, then this will be equal to this. That means total energy which is present here, this equal to the final output energy plus the loss of energy which is happened in this during the fluid flow. So that one only written. So the head at the outlet of the outlet of the nozzle, what we can write, this is the head is there. So this one we can write, because we know that kinetic energy is at this outlet point we used to consider the kinetic energy of the total energy is converted to kinetic energy. So here what is the head is there? Now that is kinetic head, that is V square by 2G. So V square by 2G plus HF. HF already we discussed many times, that is the loss of head due to the friction in the pipe. So this is the major loss. So we can write the formula for this, 4F LV square by 2GD. So this is the formula for this one. Now I can write from this equation like V square by 2G, V square by 2G equal to H minus 4F LV square by 2GD. Okay, this one we can write. Let's give this as a box one. Now we need to find out the power transmitted through nozzle. We have already found previously the power transmitted through nozzle, this one. So let's write down, but we know that, okay, let's write here, we know that the power transmitted through nozzle equal to 1 by 2 rho A VQ by 1000. This one as outlet condition, this 1 by 2 rho A VQ by 1000. So here what we'll do, we'll just put this value of V square in this equation. So V square also we can write from here, like V square, if you keep it here, 2G will be go this side and that will be multiplied here. Okay, so here what we'll do, just put the value of V square in this point. So V square value will be, okay, let me write here, 1 by 2 rho A V divided by 1000, bracket start, this is 2G bracket start again, H minus 4F LV square by 2DG. So this equation I just taken from the previous step, like here, from here. The next step is from here, we can write this is like, V square one side, and this 2G take it to the right hand side, 2G multiply of this whole thing like H minus 4F LV square 4f LV square by 2 dg bracket close. Just put this value in this equation. The same equation, what is that? The power transmitted through the nozzle. So here, next step what we can write here, let take common from this and let try to solve this one and keep the velocity terms in one side, so that next step we can go for the continuity equation conditions. So what I'll write here, this one rho g. So rho g, this g part we can take it to outside, and 2 will be cancelled here. Now see, 2 will be cancelled here. So finally what I can write, rho g a v, rho g a v divided by 1000, and the remaining part as usual h minus 4f lb square by 2 dg. Okay, so this is one equation, we can mark it. This is equation number 4, suppose. So this is the power transmitted through nozzle. So now, yeah, 4f lb square. Yeah. Now one more thing, we need to take the help of now continuity equation to find to put the value of velocity. Okay, so we know that next step we can write, we know that the continuity equation equal to AB, A1 V1 equal to A2 VT. So here we'll consider the continuity equation between this pipe flow and the outlet of the nozzle. So here we can write, in the pipe flow AB is there, and from the nozzle this is small ab. So here velocity equal to, we can write small ab by capital A. Just put this value in the previous equation, then what will get, power transmitted through nozzle equal to, we can write this rho g ab by 1000 bracket start 1, no, h is there, h minus 4f lb square, h minus 4f L. In place of V, we need to put the value of this one. So this is L A square, and this one we can write V square by A square. Denominator 2dg is there. 2dg bracket close. So this is the equation for power transmitted through nozzle. Now, when the power will be maximum, the condition is for us. What condition I have given? The condition for maximum power transmitted through nozzle. This is our main point. So when the power will be transmitted maximum, now when the derivative of P, with respect to velocity equal to 0, then we can consider this is the maximum will be there. So in this case, what we can write? We can write derivative of P means the total whole term what is there, we need to write this. That means rho g ab by 1000, and in bracket of this one we can write h. Now b part, let's take it to inside directly, or else next step we'll do that one otherwise. So h minus 4 f L square, this is v square by 2 dg, and this is a square bracket close, yeah, with respect to this is dv, this one equal to 0. Now rho gv by 1000, this one, okay, let's write in this way, del derivative of whole term rho g a divided by 1000. This velocity term, let's take it to inside. So hb minus 4fl a square, here vq will be there, and denominator 2dg by capital A square, and bracket close equal to 0. Next term is we need to do the derivative of this. So this is the constant term. What we can get it, we can just write it here, rho g a by 1000. This is the constant term what was there. Now derivative of this hp, so that will constant h will be there, dv by dv, minus here v square is there, VQ is there, sorry, VQ. Now the remaining part, all this constant term, we can take it out, like means we can, no need to derive this one, only derivative of VQ by dV will be there. So this one we can write dV is 3V square. So that means 3 into remaining term what is there, as usual we can write 3 into 4FL by 2dG into A square V square again by A square whole bracket 0. Now finally, if you see this term, multiplication is there, so this term we can take it to the right hand side and make it 0. So finally what is that, 3 H minus if you see here 3 into 4FL let me write this okay, 2 dg. This V square term is there, V square equal to AV by A. So we can write this is equal to V. So 4FL. Now we know that previously this one, see this one, V equal to AV by A. Now V square equal to A square, V square by A square. So this term we can write V square, that means 3FL V square by 2dG equal to 0. Just I put this value here because V equal to capital V equal to a small AV by A. So here V square means A square V square by A square V square by A square, this one. So I have just put the value of V square equal to this one. Now this term, if you see this term, we know that what, the head loss. So that means we can write H minus 3HF equal to 0. And here we can write HF equal to, also I can write H by capital H by 3. This is the terminology. So this one we can give an equation number 5. Equation number 5. So what you can see here, what is our condition? This equation gives the condition of maximum power transmitted through the nozzle, and what it states, the power transmitted, if you see here, HF equal to H by 3. Okay, this is not A, this is H. Okay, H by 3. So the maximum power transmitted through nozzle, when it is maximum, that the loss of head, this one, due to friction in the pipe is 1/3 of the total head of the power supplied, or total head supplied at the inlet of the pipe. This is H equal to what, capital H equal to, we have seen here, the total head at the inlet condition. Okay, so when the power will be maximum power will be transmitted through nozzle. Now when the loss of head means what, through the pipe, this is when the fluid is flowing through the pipe. Okay, the loss due to friction, when it is 1/3 of the power or the head supplied to this inlet is 1/3 of that, then only this condition will be satisfied. Though this is a slight lengthy one, but it's very simple. You can see what are the points we have discussed. So to identify this power transmitted through nozzle, first what I have given, just I have given a brief idea of what we have discussed in our previous video lecture, and there we got this equation V square equal to this root over of 2gh by 1 plus 4FL A square by A square by D. And from that we need to find out the kinetic energy equation, half mv square, m equal to rho AV, again kinetic energy per second half into rho AV cube, then power at the outlet condition, this one, kinetic energy per second. So now efficiency through the power transmitted through the nozzle, output by input. So power at the output condition, power at the inlet condition. So this one we got this equation. Now the condition for maximum power transmitted from nozzle, as I told, this is H equal to, H in the sense the head at the inlet condition. This is inlet condition, this is outlet condition. Okay, H at the inlet condition, that means what is the energy supplied to this at inlet condition to the power to the pipe, equal to the energy which is coming out at this pipe or head at this pipe, plus the losses of energy through the when the fluid is flowing through the pipe, that one. So from there we just solved it, and by using this quantity equation we just kept the value of velocity there, and finally we got this HF equal to H by 3. So this is all about the details regarding the power transmitted through nozzle. I hope you understand this lecture. If you are having still doubt or query regarding this, you can give a comment on the comment box. Thank you all.